and thanks everyone for coming. Today I'm going to talk about an allocation problem for social good. More specifically, I'm going to talk about how we can use auditing to design more efficient solutions to this problem. And this is joint work with Hu Fu and Kevin Leyton-Brown from UBC, and also Scott Kominers and Alex Wei from Harvard. The problem I'm going to talk about today takes place in the system of food banks and food pantries. So for those of you who aren't familiar with how the system works, it goes a little like this. There's a series of food pantries which are spread out amongst various communities, and these food pantries are responsible for feeding the public. All these food pantries are usually served by a single centralized food bank. This food bank receives shipments of food from donors, and it faces the problem of deciding how to allocate these shipments of food amongst the food pantries who need them. Now, there's a couple of things that make this a difficult problem to solve. The first are the difficulties we see in most mechanism design problems. The food pantries have private information about their demand, and while everyone may subscribe to the goal of feeding the hungry, food pantries would rather not run out of food than see food being equitably distributed. But what makes this an especially difficult problem to solve is the fact that we shouldn't be able to charge payments in the form of money. And there's a variety of reasons for this. For one, any amount of money that a food pantry spends on food is less money they have to pay their staff or their operating costs. Another reason is that an increase in demand does not necessarily reflect an increased ability to pay for that demand. In fact, under-resourced food pantries are often the ones that need the most food. Often in mechanism design, when you aren't allowed to charge payments, you're left in a pretty hopeless scenario. So we also make use of a couple of tools that are also common in this scenario. The first tool we're going to make use of is auditing. So auditing is not only common, but nonprofits are often obligated to observe where their resources are going and how they're being utilized. So we're going to show how we can use this information to help maintain accountability for wasted goods. The other tool we're going to make use of is the fact that food pantries and food banks repeatedly interact over the time. And the way we're going to use this is to enforce incentives by threatening to withhold future allocations. And what this is going to do for us is allow us to reduce this repeated no money problem to a single round utility maximization problem. So rather than trying to maximize social welfare without access to payments, we're just going to be trying to maximize social welfare minus payments. So the outline for our technical section looks a little like this. First, we're going to talk about how auditing can be used to improve social utility. And we're going to do this in two ways. First, by showing how auditing can decrease the payments of existing auctions, and then by showing how auditing can give rise to new optimal utility maximizing auctions. Once we've done this, we're going to show how this reduction works from the repeated allocation problem without money to the single round utility maximization case. And this is going to motivate our auditing results by giving us a way of using it for the food bank problem. So let's begin by talking about auditing. And first, we're going to set up a bit of preliminaries about our agents or food pantries. Each agent has a private type that's drawn from a publicly known prior. And what these types represent are distributions over the amount of demand that that agent might face. So for example, TI here probably needs about 2 shipments of food. Finally, we're going to call the demand that's drawn from these distributions D. And now we can show how auditing fits into mechanism design step by step. So the mechanism begins like most mechanisms. The private types are realized from the priors, and each agent decides on a type to report to the center. Then, based on these reports, the center needs to decide on how to allocate their goods, with the only stipulation being they can't allocate out more goods than they have. And this is where things take a turn when we introduce auditing. So now each agent realizes a demand from their type, and the center can observe the minimum between the agent's demand and the amount they were allocated. And you can think of this as the amount of goods the agent received that they were actually able to consume. And we'll call this observed demand. Finally, the center can charge a payment that depends not only on the reported types, but this observed demand value as well. Now that we've described our mechanism, we need to describe how agents reason about playing with this mechanism. And for that, we need values and payments. So an agent just has value for all the goods that it received and it actually consumed. So the agent doesn't have any value for goods that it received that it did not have demand for. And as I mentioned, the payment depends not only on reported types, but this observed demand value as well. Unlike most mechanism design problems, we assume that the agent's utility is quasi-linear. So it's just the value minus the payment. And then agents are just trying to maximize their interim utility. So this is just their utility and expectation over what their opponents will do and the demand that they'll draw from their own type. And then we can just use the classic BIC constraint, which says that the truthful strategy must be the strategy that maximizes their interim utility. So now we have all the pieces we need to describe our social utility objective. So as I mentioned, we're trying to maximize value minus payment. And since this is social utility, we're just summing this across agents. And this is subject to the BIC constraints I just introduced, and one additional constraint that says we shouldn't charge negative payments. And this is because the reduction that's coming later is going to enact payments through threats against future allocations. So negative payments would reflect promises of increased future allocations. And if we made too many of these promises, we would promise out more goods than we have and run up against feasibility constraints. So similar to the revenue maximization problem, this is a difficult problem to solve for the general case. So we're going to start in a simpler setting to gain some tractability. And the setting we're going to start in is the unit demand setting. So this is just a setting where each agent is either allocated one shipment of the good or nothing. And therefore, their type distribution could just be represented as a distribution over whether or not an agent needs a good. And obviously, we can represent this by a single value, so we'll just represent it by the probability the agent needs an item. Now, usually, the unit demand setting is nice because we can leverage these tools from classical auction theory to optimize over these mechanisms relatively easily. However, there's still one thing that's keeping us from being able to use these tools in the auditing setting. And that's the fact that we still have two unique payment terms in our utility function. So we have one payment for agents who receive the good and use it appropriately, and one payment for agents who receive the good and waste. Luckily, we're able to show that when your goal is to maximize utility, you actually only need to charge agents who waste the good. And intuitively, this makes sense. If you're trying to incentivize agents to use goods appropriately, you don't want to charge them when they do that. And we're going to call these mechanisms, which only use this single payment term, waste not, pay not mechanisms. And now we can derive the auditing equivalent of Meyerson's lemma, which, if you're familiar with this, this looks almost exactly the same. We now are able to characterize waste not, pay not mechanisms, and all that's changed is our payment identity. So now we have a payment identity that's specifically the amount that we should charge agents who waste. And when we work this out, it looks like the original Meyerson payment identity divided by the probability that the opponents would have wasted the good. So to gain some intuition into how this works, let's look at an auction everyone knows and look at the audited equivalent. So we're going to look at the two-agent case of second price auction. Here, the blues and greens represent the probability that the agents need items, and the red and yellow represent the probabilities they don't. So obviously, in the usual second price auction, the item goes to agent 1, and he's charged agent 2's type, which is the green portion of the circle. Now, as I mentioned, if agent 1 wastes the good, he should be charged the green portion of the circle divided by the probability agent 2 would have wasted, which is the yellow portion of the circle. But to reemphasize, he's only charged this payment when he wastes the good. So he's only charged this with the red portion of the circle a fraction of the time. And the important thing to draw from this is that it's pretty easy to see this is actually less than the payment he would have been charged under second price auction. And that's exactly our goal, is to lower the payments. However, whenever you're lowering the payments of an auction, you need to ensure that you're not affecting incentives for the other agents. So we need to make sure that agent 2 is now not incentivized to deviate and try to steal the good from agent 1. Now, in a traditional second price auction, he would have been charged the blue portion of the circle for doing this. And we're going to say that he should have been charged the blue portion of the circle over the red portion of the circle. But again, he's only charged this when he wastes, which is the yellow portion of agent 2's circle. And again, it's now pretty easy to see this payment's actually larger than he would have been charged in the original second price auction. So we haven't changed incentives for agent 2 at all. And the important thing that we can draw from this example is that the audited second price auction payments are exactly the original second price auction payments that are just scaled by this fraction of 1 minus the type over 1 minus the price. And this is important because this fraction is less than 1 for all of the types that are greater than the price. And these are exactly the agents who would have been allocated the item in the original auction. So we've decreased their payment. However, for all the agents who wouldn't have been allocated the item, this fraction is greater than 1, keeping their incentives at least as strong. And just to give an example of how much auditing can save you for payments, if we look at the uniform distribution with 2 agents, the expected winning type is 2/3, and the expected price is 1/3. So auditing cuts the expected payment in half. So now we've seen how auditing can affect the payments of second price auction, and in fact, using a similar strategy, we can lower the payments of any auction which charges a payment, including the optimal social utility mechanisms. However, there's cases without auditing where the optimal thing to do is give away the item for free. So there still remains the question of whether or not auditing can do anything to help in this scenario. More generally, it raises the question of, does auditing have a different optimal social utility allocation rule? And by following this Myerson-Lemma strategy to its logical conclusion and deriving virtual utilities, we prove that indeed you can derive new optimal social utility allocation rules, which can give you even larger gains than just altering the payments. Now let's return to the more general setting beyond unit demand. As I mentioned, this is a hard problem. We don't have a characterization even in the non-auditing case. However, what we do have are families of mechanisms which are guaranteed to work over any family of types. The most obvious one being VCG. So a natural question to ask is whether or not we can use a similar strategy to what we use in second price auction to lower the payments of VCG. And in fact, nearly the same payment rule can extend to VCG and allow us to gain even more utility. However, unlike the unit demand setting, there's not only one option for how to use auditing to alter payments. There's a large design space. And we give an example in the paper where if you fine-tune the payment rule to the underlying type space, you can get even larger gains in utility. So now that we've seen how auditing can give us large gains in a utility maximization problem, let's focus on how this reduction works from the repeated allocation problem without money to the social utility maximization problem. And we're going to do this using dynamic mechanism design. So dynamic mechanisms are just mechanisms which don't consider a single interaction with an agent, but a series of interactions over time. And let's introduce a bit of basics. So at each round, the agent's going to draw a new type from their prior, but their prior is not going to change over time. And when an agent's deciding on what the optimal strategy is to play, they consider not just their type, but also their history of interactions with the mechanism. And they must also consider not only the allocation they'll receive in the current round, but the entire future allocations they might receive. And when agents reasoning about their future allocations, they need some model of how they compare goods they'll receive tomorrow and goods they'll receive today. And for this, we assume an infinite time horizon without discounting. This just means that the interactions between the food pantries and food banks have no end in sight, and a food pantry values the food they're going to receive today as much as the food they'll receive 3 weeks from now. And we're left with a few choices of optimality criterion in the infinite time horizon setting, and we choose the overtaking criterion. And we choose this just because it gives us resolution over finite deviations in strategy. Now we can introduce the family of dynamic mechanisms that's going to make this reduction possible. And we call these mechanisms debt mechanisms, and they're specified by 3 components: an underlying single round mechanism M, and 2 constants, an allocation length and a debt rate. And each interaction an agent has with the debt mechanism can be one of 2 types of rounds. Either an agent's in an allocation round, and in an allocation round, an agent is allocated based on the underlying single round mechanism, and he's charged a payment accordingly. But rather than being charged with money, this payment's just accumulated as debt to the system. And these allocation rounds always occur in consecutive batches of size the allocation length. The other type of round an agent can be in is a punishment round. So in a punishment round, an agent's guaranteed to be allocated nothing, but rather than being charged a payment, his debt is reduced by the debt rate. And the agent is forced to participate in punishment rounds until he's paid off the entirety of his debt to the mechanism. So let's run through an example of how a debt mechanism works with a debt rate of 4 and an allocation length of 3. And we'll just choose an underlying single round mechanism that's simple and doesn't use auditing. So of course, the debt starts at 0. And in the first round, maybe they're allocated and charged a payment of 5. And in the second round, maybe they're allocated nothing, so therefore they're charged nothing. Finally, in the third round, maybe they're allocated again, and this time they're charged a payment of 3. Now, they've reached the end of their allocation length, and they've accumulated a debt of 8. So now they must enter a punishment round. So in the punishment round, they're guaranteed to be allocated nothing, but their debt is reduced by the debt rate of 4. Now they still have debt, so they're forced to participate in another punishment round to, again, reduce their debt to 0. And now that their debt is at 0, they're allowed to return to participating in allocation rounds. And what we find with debt mechanisms is that if we choose an underlying single round mechanism that satisfies BIC constraints, and we set the debt rate equal to the expected utility of this underlying mechanism, we get exactly the reduction we need. We get that the average welfare generated by the debt mechanism is equal to the expected utility of the underlying mechanism. And this means that we can substitute in the auditing mechanisms we've derived earlier to get good social welfare in the food bank and food pantry problem. Now, before I wrap up, I just want to mention that working in this charitable setting gives you access to a bunch of tools from a bunch of different areas of literature. So here's just a few examples in the fields of utility maximization, repeated allocation without money, and auditing-based payments. So in summary, we've shown how to leverage auditing and repeated interactions to design efficient solutions to the food bank and food pantry problem. And we've done this in 2 ways. First, by showing how auditing can not only lower payments, but give rise to new optimal utility maximizing auctions. And then by showing how debt mechanisms can reduce this repeated allocation problem without money to a static utility maximization problem in which we can use auditing mechanisms. Thanks. So in the multi-agent case, to keep incentives, we need to sample people's types so that they don't know. So if there is a difference between total demand and sample demand, we do have to throw those goods away. But we leave it open in the paper as to whether or not you can come up with a clever solution, like having some sink agents for that wasted food to go to, or some clever way of redistributing these goods that doesn't affect incentives.